justified it. You want to work on something that's real. Like you don't want to work like the whole point of everything is leading up to this area. I don't want to give you a dumb problem that has a pendulum swinging that no one really cares about. You know, the physics problems. Mm-hmm. Mark, you might see this. It's like, you know, there or the particle that's going around and like who's ever seen a particle moving around? You don't really care that much. But really what I think really governed a lot of the mathematics in the 1950s that drove the education that you have today is the idea of modeling the atmosphere. And I'm not going to put the equations up here because they're really, really nasty. But that's kind of where everything comes from. And calculus, the powerful tool of calculus and how it's going to be applied, the way you learn pre-calculus was all kind of set up to get to this place. So aerospace engineering math, basically, they still do they still use those tools to build everything they're building up. Those engineers go to Boeing and places where they're building planes. So there's a whole need for this. I saw a really interesting book. It was on the Navier-Stokes equation to look at a deliberate release of anthrax in Russia. It actually happened like this. Something it wasn't deliberate, but there was an accident, and they wanted to see if the Navier-Stokes equations actually would model the path of the anthrax, and it did. Back then, they were numerically using things like Runge-Kutta, but you literally had to code it in Fortran on these punch cards and then take the punch cards to some person who ran the stuff, and you had to hope all your code was correct because it would take days for the punch cards to be filed. So you wouldn't know what your outcome was until like a few days later. And they published this into this book, and you can see the drawn things. Now, what they were using was a system called the Navier-Stokes equations. And they are partial differential equations. So what's a partial differential equation? A partial differential equation is something, did you guys cover any of this have you seen this before? A little bit in Jedi math, maybe? Okay. So you probably saw simple things. We don't teach this class all the time, the partial differential equations course, but it's a great course to take if you're interested in this kind of math as an undergrad. It has a lot of theory that's backed up behind it too. So if you like the theoretical side, that was actually what my degree was partial differential equations on the theoretical end. But basically the idea is you have, I'm not going to give you the Navier-Stokes because that's really physics heavy because you're trying to really capture the three-dimensional flow inside the atmosphere. So that's a really difficult thing to do. But they're governed by laws of physics. That's kind of why I mentioned physics. Newton's second law of motion. All these models are laws that you learn about in basic physics. They're used to develop these equations. And so you'll start with fluid flow type because the air is a fluid. So you'll start with those kind of laws and then build up these equations. But you can think of a simple equation. This is one of my favorites. A lot of times you can imagine you'll want something to diffuse or maybe something not to diffuse. A good example is the human body. When they develop drugs, they'll want to know like if you consume something or if you inject something, how does that diffuse through your body? So that these are the kind of things we use diffusion models for. But if you have a diffusion model, let's make it two-dimensional because you can see it. But you typically in a PDE class you start with just one dimension, a rod and something like a flame that's on one end of the rod and the heat is flowing through that rod. But that's kind of like the particle. You just can't really see it. It's a made-up example. It's not a made-up example, but it's an example that is kind of, it's a toy problem. The real problem is you have maybe a sheet of metal and you have a flame underneath that sheet somewhere, and you're capturing the temperature across this sheet of metal as that flame is holding a spot center. So I don't know why we use use, but we use usually for a PDE. T is time. Let's say minutes, put a unit on it. And X and Y is the location on the sheet of metal. And this is the temperature at time T and location X. This has been used in all kinds of examples. Like I saw it used to describe how rabid foxes might diffuse in a population. So now the sheet of metal becomes the United States, a geographical map. You have a point source where you first saw rabies, so you kind of know like where it started. Foxes with rabies will tend to spread, unlike the usual foxes that stay together, and then they spread across the United States in like a diffusive pattern. So they'll use this kind of a model, same like the temperature. The diffusion constant would be very different than a sheet of metal. But the model is ut, the partial derivative of u with respect to t, is equal to d, that's called the diffusion constant, times the partial derivative of u with respect to x, second derivative, the partial derivative of u with respect to y, second derivative. So this should, to your eyes, look a lot more complicated than anything we've done in this class. But that's where the good stuff is. That's where you really model things that, are interesting. We actually had written a model with to talk about the trajectories of obesity prevalence in the United States. And I kind of mentioned that, hey, it's not uniform across the United States. Like we're just taking the United States as one group and then just making some assumptions and writing a system of ordinary differential equations down. Really, you have different pockets that are doing different things, and the diffusion is not the same everywhere, so you kind of need a PDE to really model this correctly. And one of my co-authors said, well, how many months would that take us to do? I'm like, 2 years? Like, I don't even know what that model would start to look like. I would have to think about it. Writing down the model alone would probably take me a year. But that's the kind of example where it's more reality. It takes in more of what accounts for everything. So Navier-Stokes is this thing on steroids. Like it has a lot of different layers to it. It's complicated. There was an entire journal dedicated to just particular solutions of this Navier-Stokes equation. So you can't solve it by hand. Back then, they were developing specific numerical methods to handle and treat certain things. So it was not even, you can't even apply Runge kata to it. Like that doesn't work. Typically for a PDE, you need an interesting PDE. This one's not too interesting, but an interesting PDE, you need a specific numerical method designed for that PDE. And for the Navier-Stokes, you need a specific numerical method for different cases of the Navier-Stokes equation. Okay, so why am I bringing this up? We're not going to do PDEs in here. Another thing that was going on around the time that computers were first available to researchers, so people were trying to model the weather. They believed or they felt like if we just had a big enough computer, and back then it's like Star Trek, they had huge computers in the background with spinning wheels that made noises, and you kind of see pictures of these old computers, but they were not accessible to everybody. But the question was, if I had enough data and I had these Navier-Stokes equations and the right model, could I predict the weather? Because if I know that these equations govern the atmosphere, then I could potentially predict the weather, and that would be a huge thing. As you know today, from our little charts that we get, or our apps we get, it's really hard to predict the weather. And it's because of a few things. There was a meteorologist by the name of Edward Lorenz, and he took this Navier-Stokes equation and he used something called the method of lines. So like you basically in the spatial piece of it, you just fix and look down one line. And if you look down one line, your x component would be fixed on a vertical line. So you've simplified the original thing to kind of look along this thing called just a line. And if you do that, you don't have a PDE anymore. You have an ODE along that line. So he just whacked off a whole bunch, like a Taylor series. You just whack off the top part of the Taylor series. He just whacked off a whole bunch of those ODEs that he got from putting the lines down and just kept it to 3. So I got it in my head as I was prepping for this week that it would be cool if we looked at that system. It's just 3 equations. It's nonlinear, so it satisfies what you're doing in the book. And we do linearization of the Lorenz model. It turned out that this is incredibly hard, but I already committed. So I'm going to walk you through it. And then I gave you something to work on called the van der Pol equation. The story of Edward Lorenz is really interesting because I heard it from his own mouth. So he's not alive anymore. But when I was a junior in college, I went to a research experience for undergrads. And the guy that was running it said he won't be able to meet us today because he's having lunch with Edward Lorenz. Back then, chaos theory was everything. Like it was in the news. Someone was talking about it on the floor of Congress. And, Jurassic Park just came out. Edward Lorenz and the Lorenz butterfly was the thing that everybody wanted to generate on a computer. And I asked him, can you take us to meet Edward Lorenz? And so he did. And so Edward Lorenz told us about the paper that he wrote where he discovered that you really can't predict the weather. And he discovered it from this model of 3 equations. So I'll show you some simulations of that today and how bizarre it is. But what happened was it's a 3-dimensional equation, so you have a 3D plot. He ran it through Fortran, did the punch cards, got it back, saw what was there and said, something must be wrong with my code. Because what he kind of saw was that there was like these slight differences he had in the initial condition, and it led to really different results. But what that's telling you is if there's a slight perturbation somewhere in Ohio in the atmosphere, it could affect the weather in New York State maybe a year later. So those trajectories will diverge from each other. That's what we call sensitive dependence on initial conditions. So he was seeing it, thinking he made an error in his code, went back and ran it again and saw it again, and he plotted these by hand. So I think Wednesday, I'll bring in, I have a framed picture. I ran it on Mathematica. Mathematica was just a commercial product that started right then. I learned how to use it, wrote the code for running Lorenz model on there, and had him sign it. Like that was the best I could do. They didn't have a book, and there was no way to print the paper. We didn't have printers sitting around everywhere. But I got that. It's framed on my wall. If you walk into my office, you will see it directly at your eye level. So personality dictates that I want you to see that when you walk in my door, because I'm really, really proud that I got that picture and I got him to sign it, and I had that conversation with him. But what this is the precursor to the whole field of dynamical systems. And you have a course offered next fall called Chaos and Fractals. And it's taught by Dr. Groth, I think, or Dr. Moen. One of those 2 is teaching that class. But she's using the first textbook that was written that was encompassing for an undergraduate. I learned out of it, and she's using that same textbook. But that actually became a field in its own right, probably around the 80s. So this was published around 1963, the Lorenz model. So it kind of tells you how long it took this whole area to become a field enough that you had a book that could be taught to undergrads. Not a very good book, but you can learn from bad books sometimes. We're learning from Barbel's not a very good book, but we're learning from it. But that class is amazing. What he was seeing in the Lorenz model was something called chaos. It wasn't really coined till several years later, and they had a formal definition of when you see chaos in a model. And that was done by my academic grandfather, Jim York, in the late 1970s or early 80s, somewhere around there. He coined that term chaos. So that all was in my lifetime, this new area of math. So I think it's a really cool model for us to work on. And I'm going to show you today how do we understand these nonlinear models using what we know already from linear stuff. That's pretty much how we do everything. Think about calculus. You take nonlinear things and you model them in tangent lines, right at that point. So we're going to do that. We're going to do a multidimensional tangent line, a version of that, and I'll look at the Lorenz model. So very cool. It just turns out that solving for the equilibrium